Okay, so in this video we're going to solve a Riemann sum using 30 right rectangles to approximate the area of the shaded region. We see the shaded region goes from x equals -1 to x equals 2. And it is bound by the x-axis and the curve of the function f of x equals 9 minus x squared. Well, our first step is to find our delta x, which the formula is b minus a over n. B is the right side of our interval. A is the left side of our interval. So we have 2 minus -1. N is the number of rectangles. So we get 3 over 30, or delta x equals 1/10. Now we want a generating function for the x values. We call that generating function xi. And for a right rectangle approximation method, we use a plus I times delta x. This is the left endpoint. This is the number rectangle we're on I, the ith iteration, and this is our delta x, which is 1/10. So xi is equal to -1 plus I over 10, and I'm just going to rearrange it as I over 10 minus 1. Now we want to plug that into our function f of x. So since f of x is equal to 9 minus x squared, f of xi will be equal to 9 minus, and then in parentheses, I over 10 minus 1 squared. So we took all of xi and we plugged it in for x. So we replaced the x with the expression for xi. Now we would like to FOIL this to simplify the algebra. So f of xi is equal to 9 minus, and when we FOIL this, we get I squared over 100 minus 2I over 10 is I over 5 plus 1. So that has been FOILed, and now we can distribute this negative through the parentheses. And we have f of xi is equal to 9 minus I squared over 100 plus I over 5 minus 1. We can combine the constants and say that f of xi, 9 minus 1 is 8, minus I squared over 100 plus I over 5. Now we would like to insert this information into our area formula. Our area formula is delta x plus the sum of xi's. So this is the width of each rectangle, and this is the sum of the height of each rectangle. So we can say that area is equal to 1 over 10 times the sum, and we're going to take everything for xi and plug it into there. 8 minus I squared over 100 plus I over 5. Recall our summation formulas. Said if we had a constant, then we can replace the summation formula with the constant times the upper bound of the summation formula. We are doing from I equals 1 to 30 rectangles. So our constant would simply be 8 times 30. Our I squared and our i's will have their own formulas. And we're going to use each of these formulae to rewrite this summation. So now I can say area is equal to 1 over 10 times the sum of 8 from I equals 1 to 30 minus 1 over 100. I separated that out, times the sum of I squared from I equals 1 to 30, plus, I'm going to take this constant out also, 1 over 5 times the sum of I from I equals 1 to 30. Now I can replace each and every one of these summation expressions using the appropriate formula Remember, n is the upper bound, so anywhere you see n, I'm going to replace it with 30. So this first summation is simply 8 times 30. Here's my 1 over 100. The I squared formula is going to be 30 times 31 times 61 over 6. And then I have my plus 1/5. And the I formula is going to be 30 times 31 over 2. And if we simplify this, we get 240 minus 94.55 plus 93. And if we add all of this up and multiply by 1/10, we get 23.85. And the definite integral answer, which is the exact answer, is 24. So we see that 30 rectangles gave us a good approximation. And this is the exact. So there's your example of using summations with Riemann rectangles to approximate the area of the shaded region under the curve.